So welcome to Math140 Calc 2. This is lecture 15. And what I want to do today is I want to talk a little bit more about partial fractions, which I think is the worst of the integration techniques. So the nice thing is we're going to get the absolute low point of the semester done before spring break, and it'll be out of the way. There will be integrals that are even worse than this, but they're so bad they can't even be done. So in some sense, it doesn't really matter that they're worse, but they can't be done. This is the worst of the integrals that we can actually do in closed form at the end of the day. And then if there's time left over, I will talk a little bit more about some problems from U substitution. And so I've just got a standard list of here's a couple of ones I've mentioned, and we can always go back and just try to do a few of these ones later if there is time. Okay. So the whole point of partial fractions is to try to reduce integrations involving denominators to simpler things. This is a fundamental idea in all of science. You break a complicated object up into simple things. So I think we had somebody talking about taking a chemistry class at 8 a.m. today. And so you've got your molecules broken up into atoms, where you can have atoms coming together into proteins, and depending on just what level you want to break things down into. In number theory, we break things down often into prime numbers. Write numbers of product of prime factors. So we want to figure out integrals over fractions. And the simplest fractions are going to be of the form specific partial fractions. So we want something of the form integral 1 over f of x to the m dx, where f of x is not factorable. And of course, we might want to consider more generally the integral of g of x over f of x to the m dx. So we want to look at stuff like that. Okay. So let's start trying to look at some simple cases. So always start simple. What's the simplest choice you can think of for f of x? That'll allow you to look at x, right? The simplest I'll let you do is x. So if we take f of x equals x, I want the integral of 1 over x to the m dx, or I can write that as the integral of x to the negative m dx. Do we know how to integrate that? Do we know what function has derivative x to the negative m? So what function will have derivative x to the negative m? Negative x to the negative m plus 1 over what? So what do we want to divide it by? With the negative sign outside. Negative m plus 1. Because now when the exponent comes down, it's going to cancel that. But if I'm actually writing negative m plus 1, I don't need the negative sign outside. So if I want to pull out the negative sign, it would then just be m minus 1. You want the minus sign. Okay. Or if I want to get rid of the minus sign, doesn't really matter. Is that the answer? Do I have to be careful with it? What is the danger? M is a constant. So whenever you see, yes. Yes, we need m not equal to 1. And so if m equals 1, then we're integrating 1 over x. What's the answer in that case? So if we have the integral of 1 over x, what function has derivative 1 over x? Natural log of x or log of x. So if I give you 1 over x, it's not that hard to integrate. This is one of our standard functions. Okay. So now let's try to do something a little bit harder. The next thing I could try to do is the integral of 1 over, say, ax plus b dx. There's a couple of ways to do this. I could pull the a outside the integral. I could write this as 1 over a, the integral of 1 over x plus c dx, where c is equal to b over a. So really, it's sufficient to figure out how to integrate something to the form 1 over x plus c, because if I had a coefficient in front of the x, I could just pull that out. So again, I'm just trying to make things as easy as possible for myself. I could, of course, just do things more generally. I could do u substitution. I could let u equal ax plus b. What would du dx be? If u is ax plus b, du dx is a. Right? And then that means du just goes away. Does anybody know who the Bonds is? Cultural history credit. Happy days. Here was my commencement speaker. Yes. So if du dx equals a, that means du equals a dx, or dx equals 1 over a du. Which do you think is going to be more useful for this problem, solving for du or solving for dx? Yeah, solving for dx. You don't have to write du dx equals a. You can go straight to du equals a dx. It's just a question of which is more likely to get the answer right. So our integral is going to be the integral of 1 over ax plus b is 1 over u, and then dx is just 1 over a du. So that's going to just be 1 over a integral of du over u, which is just 1 over a natural log of u, which is just 1 over a natural log of ax plus b. If you want, we could put a plus c if we wanted, because we're doing an arbitrary integral. But the whole point is, if I give you something in the form 1 over ax plus b, it's really not that much worse to integrate that than integrating 1 over x. I just do a u substitution, and then I just substitute back at the end of the day. So any questions about how to integrate something in the form 1 over ax plus b? We're trying to slowly increase the complexity of it. Okay, what's the next one we could try? So we did f of x equals x, ax plus b. Let's try f of x equals what? What's the next one to try? Actually, we did x to the m. What should we try now? So we could do that. I'm going to try a simple one first. I'm going to just try, say, maybe ax squared plus c.
Are we going to do 1 over that?
We'll do 1 over that because we're always integrating 1 over x. So here's why this isn't a bad thing to do. So if we have the integral of 1 over ax squared plus c dx, I can pull out the a, and it's the integral of 1 over x squared plus c over a dx. Correct? Everybody comfortable with pulling out the a? Now what I'm going to do is let u equal the square root of the absolute value of c over a times x. So I drew it the other. I think I went the other way. I want x to equal the square root of c over a times u. So x squared is the absolute the absolute value of c over a u squared. So this is where it's a little bit painful. I have to be careful about the sign. I don't want to be changing variables by multiplying x by the square root of -1. So let's break this up into cases. Let's assume C over A is greater than 0, and let's assume C over A is less than 0. So one case is we have the integral of 1 over x squared plus, let's call it plus A dx, and the other one will have the integral of 1 over x squared minus A. And both of these, I'm going to write it like this so that A is greater than 0. And now, if I let x equal the square root of AU, then dx is the square root of A du, and x squared is going to be AU squared. I can now pull out an A, and I get 1 over big A, 1 over u squared plus 1, dx becomes root A du. So I get a square root of A on the side, or square root of A over A integral of 1 over u squared minus 1. So the whole point of this is that if I give you something with a form 1 over ax squared plus c, I can reduce it to one of the following two integrals, integrating 1 over u squared plus 1, or integrating 1 over u squared minus 1. Once I know how to do those two, I can get anything of the form ax squared plus c. Sometimes, rather than memorizing a process and memorizing the result, it's better to just remember how to do it and just do it from scratch. So rather than remembering how things change, if I have a positive sign, I'm going to go one way. If I have a negative sign, I'm going to go another way. And the advantage of this is I only have to do two integrals. So the more integrals you know, the better. I still have the table of integrals I was given when I was a senior in high school to remember it. I think the sheet is actually even still readable all these decades later. I try to remember to bring it to class. But there was a certain, if you remember these integrals, then you can pretty much get all the standard ones that are going to come up. With a little bit of work, you can manipulate something so that it looks like one of these. The question is, how comfortable are you doing the manipulations? Programs are getting better and better and better at doing these manipulations for you, and just knowing that you can recognize that this is this and give you the answer. How many of you have ever used voice identification software to talk to a real live computer? How do the computers do in talking to you? Have you ever used an automated computer system and talked to it? Or just you're calling up to make a reservation or to do this or that. How often does it do a good job? How does it do with your accent? Okay. Okay. I've found that for the most part, it's now fine with my Boston accent. When they started with my inability to say there was definitely some trouble, and I just prayed that none of my identifications had an R in it. But now the computers catch it without too much trouble. The technology has gone leaps and bounds in the last decade. It's the same way for computer software in terms of recognizing integrals. There's so many different ways that you can manipulate things. The computers now have a lot of that stored and they can quickly do that. And so the skill of being able to do this is not quite as important as it was, but it's still worth knowing how can I reduce something complicated to something that I already know. And here are some tricks. So if I give you something in the form ax squared plus c, I can reduce it to one of these two integrals. Does anybody remember what the first integral is? We normally write it as 1 plus u squared rather than u squared plus 1. Anybody remember what function has derivative 1 over 1 plus u squared? It's not cosine. Well, the derivative of cosine is sine, but it does involve trig, but it involves inverse trig. It is inverse tan or arctan. So the integral of 1 over 1 plus u squared du is arctangent of u. And you could do this by the substitution. Could do u equals tangent theta. Du is going to be the derivative of tangent is secant squared theta, d theta. And then cosine squared theta plus sine squared theta equals 1, divide by cosine squared of theta, and that gives you 1 plus tangent squared of theta is secant squared of theta. Substitute. You get the integral of 1 over 1 plus tangent squared becomes secant squared. And then du is just secant squared theta d theta. You know, life is really good. The secants cancel and you get just d theta. And so the antiderivative of 1 is going to just be theta. But that's arctangent of u. Since u equals tangent theta implies arctangent of u is arctangent of tangent theta. So if I give you the integral of 1 over 1 plus u squared, we know that this is arctangent. So we know how to do this. Okay, so now we have the other one to do. So we now have to do the integral of 1 over u squared minus 1 du. There are two ways to do this. There's the painful way of doing trig substitution again. And now we have to look at, all right, so I have u squared minus 1. I probably want to take the like 1 plus tangent squared is secant squared. So tangent squared is secant squared minus 1. So maybe try u equals secant theta, and then secant squared of theta minus 1 equals tangent squared of theta. Maybe something like that would work. But the whole point is, does anybody remember what I said should be true about the function f of x that we're looking at? All the way at the beginning of the lecture. What did I say is true about when you're getting 1 over f of x? It's non-factorable. What do you notice about this function 1 over u squared minus 1? Yeah, this factors. U squared minus 1 is u minus 1, u plus 1. So we can actually do partial fractions here. So 1 over u squared minus 1 would be a over u minus 1 plus b over u plus 1. And this is the power of partial fractions. You reduce a complicated interval to an easier one. You take a high degree, quadratic, and reduce it to a lower degree, linear. And so now when we cross multiply, we get a u plus 1 plus b u minus 1 over u squared minus 1. So 1 is equal to a plus b times u plus a minus b. And this is true for all of u. Because it's true for all of u, what's a good value of u to try? 0. And so we try u equals 0, we get a minus b is 0. Another way of looking at this is, because this is true for all u, the coefficient of u has to be 0, because the left side has no u dependence. So we get, we haven't used this coming well, so this has to be 0, this has to be 1, so this implies a minus b equals 0, or a minus b equals 1. So a equals b plus 1. And this is 0, so that implies a plus b equals 0, or a equals negative b. So negative b equals b plus 1. So negative b equals b plus 1. Therefore, negative 1 equals 2b. So b equals negative a half, and a equals 1 half. And so now we've reduced this to integrals we already know how to do. Any questions about this problem? So just finishing the details, we would have the integral of 1 over u squared minus 1 du would be the integral. I put a with u minus 1. And a was, I think, a half. So the 1/2 over u minus 1 du plus the integral minus a half over u plus 1. So this would just be 1/2 the natural log of u minus 1 minus 1/2 the natural log of u plus 1. You have to be careful. Must make sure u minus 1 and u plus 1 are positive. That's taking logs. So this is where you have to be a little bit careful. We've talked about this before. So if it was negative, I would actually multiply by a -1. I can just have that outside. So we've now handled all quadratics. Did we handle any quadratic in the denominator? Did we do that, or did we only do special quadratics? What do you think? Well, what quadratics did we look at? Did we look at an arbitrary quadratic? We looked at forms of the form ax squared plus c. So we did not consider an arbitrary quadratic. So we want to consider f of x equals ax squared plus bx plus c equals a x minus h squared plus k. Does anybody remember what I've just written? I'll bring back any recollection from algebra 2. What is this called? Excellent, vertex form. And so you have the vertex is hk. And you can see that when x equals h, y equals k. And for any other value, x minus h squared is going to be positive. And so if a is positive, this is going to be the minimum and will point up. If a is negative, it's going to be the maximum and will point down. So this is vertex form. Why is this useful? Well, if I have the integral of dx over ax squared plus bx plus c, I can write that as the integral of dx over a x minus h squared plus k. And let me just go through the substitutions very slowly. Let u equal x minus h. Du is just dx. So the integral is the integral of du over a u squared plus k. And we just did that. So if I have something in vertex form, I can immediately reduce it to an integral I've already done. Of course, if I can factor the quadratic, then that's even better, and I can use partial fractions. But when I'm factoring it, I have to have 2 real roots. So if I give you something that doesn't have 2 real roots, I can't do this. But the more general quadratic can be handled by using vertex. Do you think we could probably do something for a cubic? As the degree gets larger, it starts to get harder and harder. What really saved us was that we had these trig identities. So when we had 1 over u squared plus 1, we got that as arctangent. So if I started to have a cubic and I had like u cubed, I don't know. So you always want to know, why did the miracle happen? What is responsible for the success? And what's responsible for the success here is the trig living in the background. We can do sums of squares, we can do differences of squares. We start getting to cubes, and there are almost surely formulas that we can do, but it gets a little bit more involved. Okay. Should I be nice or not nice? Nice, okay. So let's be nice. let's consider the integral of f of x over f prime of x dx. I claim that this is actually a nice integral to do. You do a good u substitution. Any thoughts on what we should take for u? Yeah, take u to be f of x. What's du? Dx. And so our integral is going to be the integral of 1 over u du is the natural log of u. Again, worry about sine, which is just the natural log of f of x. So if I give you something with the f prime of x over f of x, it's actually pretty straightforward to integrate that. So, for example, if I give you, the integral of x squared plus x plus 1, and I give you, 2x plus 3 dx. I could write this as the integral of 2x plus 1 over x squared plus x plus 1 dx plus the integral of 2 dx over x squared plus x plus 1. So I've split the numerator 2x plus 3 into 2x plus 1 and 2. Why would I do that? Yeah, so the first one now just becomes the natural log of x squared plus x plus 1. And then this one over here, but we've at least made it simple. As we said, hey, there's part of it that I can do and just throw out. And now rather than having a numerator that involves 2x that involves the linear term, I can make it a little bit simpler and just throw that out. You don't have to do this, but if you see stuff like that, you can often make your life easier. Does x squared plus x plus 1 factor nicely? X squared plus x plus 1 does not factor nicely. So if we were to try to do partial fractions, that doesn't factor, so I would probably do maybe like a vertex form and approach it that way. Just because I can do something doesn't mean I want to do it, right? But at least I have a recipe to do it. If you had to find the roots of a quadratic and your grade depended on it, could you do it? No. If I give you coefficients that have 3, 4, 5, 6 digits, you may not be thrilled about squaring and multiplying and subtracting and taking the square root, but you could do it. It's the same thing here now. We know the basics of partial fractions. We know certain key integrals. And if I am giving you something, I just keep working at it until I get into one of the forms I know. The more forms you know, in some sense, the easier it is, because then at some point you reach something you know. Have you ever played the Kevin Bacon game? Anybody know what the Kevin Bacon game is? What is the Kevin Bacon game for cultural extra credits? Yes. Good. Right. So certain movies are great because they have a lot of celebrity, guest appearances. The Muppet movie, for instance, one of my favorite movies. Absolutely wonderful because you have so many big stars coming in for just a few quick short scenes. Any Star Wars fans? Who does the voice of Yoda? Frank Oz, who is also one of the Muppets. Miss Piggy, yes, Frank Oz. And so, with Frank Oz, you get Yoda, you get the Muppets, you get Blues Brothers. You've got a lot of movies where Frank Oz just has a very small role. So there are certain movies that are just really good to go to. And if you can get to one of those movies, there's a lot of things you can get to. It's the same thing when you're doing this stuff here. You want to know as many different ways of rewriting. The more ways you know, the more likely you are to choose something that will work. So my Bacon number is, I think, 6 or so. I have to go through one of the premiers of Canada. Just a story. So it is amazing how quickly you can get to different people. Let's talk more about more general theory now. So now let's consider the integral of g of x over f of x dx. And we'll assume right now that f of x doesn't factor. Okay. If the degree of g is greater than or equal to the degree of f, we can write g of x is equal to, say, a of x, f of x, plus b of x. Or actually, wait, I guess the more standard notation is to use q and r. Q for quotient, R for remainder. And so the whole point of this is, well, if I have g of x over f of x, any multiple of f of x I have is easy to integrate. Because I just divide by the f of x. And that would give me the integral of qx f of x plus r of x over f of x dx, which is just the integral of q of x dx plus the integral of r of x over f of x dx. And the whole point is when I'm trying to do partial fractions, I can always assume the numerator has smaller degree than the top. So here, the degree of r is less than the degree of f. So for example, if I have, x cubed plus 4 over x squared plus x, I can write x cubed plus 4 as some multiple of x squared plus x. So what would I have to multiply by? Well, clearly I need to multiply by x, and that will give me x cubed plus x squared. Right? And now, what else do I put in? So if you really wanted to do this, we had x cubed, was it x cubed plus 4 over x squared plus x? X cubed plus 4, well, actually, let's do it the right way. X cubed plus 0x squared plus 0x plus 4. Anybody remember what this is called? Polynomial long division. I want to get the x cubed, so I multiply this by x. X squared times x is x cubed. X times x is x squared. I subtract. And so I get negative x squared. I bring down 0x. What do I have to multiply by? By negative 1. And then I would get negative x squared minus x. I subtract that. I'll be left with x. Now I bring down the 4. And so, I can't multiply x squared plus x by anything. Did I make a mistake?
No.
Okay, so I would get x cubed plus 4 is equal to x squared plus x times x minus 1 plus my remainder, which is x plus 4. And if you multiply it out, you will see that it is x cubed plus 4. You can also use, synthetic division is just another way of writing the long division. So if you ever need to do something like this, this is how you do calculations like this. And there's a reason now why you probably learned that. Is that if we wanted to do something like partial fractions, we could figure out if the numerator is very large, we can just remove parts of it. And the whole point is we only have to develop a theory of partial fractions when the numerator is of smaller degree than the denominator. Because if the numerator has a larger degree, we can just get rid of it. And so what we did is over here is if the numerator has a larger degree, write g as q of x times f of x plus R of x. And when we substitute in, q of x, f of x plus R of x over f of x, well, the q of x, f of x over f of x just becomes q of x. That's a polynomial. We know how to integrate a polynomial. And then we're left with R of x over f of x. So we have to figure out how do we integrate the general case where R of x is of small degree. And degree is the highest power of x that occurs. If R of x happens to be f prime, that very special case, we actually know what the answer is. But in general, this is where we use partial fractions. Any questions on what we've done up till now? So now, partial fractions. The degree of the numerator, we can assume, is less than the degree of the denominator. And it all comes down to how the denominator factors. So if I give you something integral of R of x over, say, f1 of x to the d1 dot 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 fk of x to the dk. What is this? I didn't write down the general form, but I would rather just write it down in a few special cases and hope that you can see the pattern rather than just overwhelm you with a tremendous amount of notation. So you're here, I've got a bunch of factors, maybe k factors, and each one occurs to a different pattern. And so, for example, let's say I give you the integral of R of x over x squared, x minus 1 cubed, x plus 2. Then, actually, let's do x squared plus 2. What would this equal? What I want to do is I want to write R of x over x squared, x minus 1 cubed, x squared plus 2, something over x plus something over x squared plus something over x minus 1 plus something over x minus 1 squared plus something over x minus 1 cubed plus something over x squared plus 2. Those are all the possibilities. I want pureness in the bottom. I want things to be pure. I don't want to have cross terms like x times x minus 1. I want to just have a nice function, f of x to the first part, to the second part, to the third part, to the fourth part. Those were the things we were looking at before. For the most part, right now, we only know how to handle factors that are either linear or quadratic. So if you have a cubic factor, take more calculus. There's a limit to how much pain I want to cause you. As a professor, there's a certain level that's mandatory, and you're beyond that, I'm happy. Did I tell you the cylinder problem from when I taught at Princeton? So in multi-variable calculus, one of the problems that my students had to do was you have two cylinders intersecting at right angles and calculate what is the volume of the region of intersection. And at the end of the semester, I wanted to know, because this was interesting to me, how many of you liked problems like that? No one liked them. And so I said, okay, should we remove those problems from the curriculum for next year? What was the answer? What do you think they said? No, of course they said no. Why did they say no? To torture everyone else. And that's when I smiled and said, how many years in a row do you think I've asked, should we remove this from the curriculum? No one was ever the first class to say, let's save the next generation. Right? There's a limit to how far I want to push this. I am fine if you can do by hand, polynomials that factor with the denominators have degree no more than 4. Of course, you can do more at higher degrees, but let's just leave it at this. This is more than enough. And just be aware that a more general theory can exist. Now we have to figure out what comes up there. And so for the first one, the rule is you're always a polynomial of degree 1 less than the base polynomial below. So numerators are 1 degree less than the base polynomials. So in the first one, we have a polynomial that's x. What's the degree of x? 1. So what's the degree of the numerator? 0, which means it's a constant. I'll call it a. For the next one, what's the degree of the base polynomial? No, base polynomial. Base polynomial is 1, it's still x. So what would be the degree of the numerator? 0, which means it's a constant. I'll use the letter b. In the next one, what's the degree of the base polynomial? It's 1, so I'll just call it c. The next one, x minus 1 squared. The base polynomial is still degree 1, so I'll call it d. Really not happy about what's about to come up. What comes next? Yeah, do I really want to use the letter E? Not really. So I will jump to F. I do know my alphabet. And then what would I do for the next one? The x squared plus 2. What's the degree of the base polynomial? 2. So the numerator is degree 1, so it's gx plus h. So I then just have to figure out what are the choices of A, B, C, D, F, G, and H, such that this works out. Yes. Because this one over here is x squared. This one here is x minus 1 squared. This one here is x minus 1 cubed. This is the base polynomial, the x minus 1. And then the other thing is the x1, it's the power, it's the number of times we have it. So I really only have a polynomial of degree 1, I just have it twice. Let's look at things a little bit more general. So let's say we want to compare, a over x plus, bx plus c over x squared versus a over x plus b over x squared. Because you might be saying, come on, I should really have bx plus c because it's an x squared. So let's do some algebra. So when I multiply, this becomes ax plus bx plus c over x squared. Actually, let me use different letters over here. So I'll use capital letters on this side. I'll use A, B. And over here, I would have ax plus b over x squared. We're trying to get something of the form. The goal is, r of x over x squared. R of x is degree 1. Right? We're trying to get something with the form something over x squared. So maybe we want this to equal 3x plus 17 over x squared. If you look at what's going on, in this case, we get, this is a plus b x plus c over x squared. This is still ax plus b over x squared. So now we get a plus b equals 3, c equals 17. Here we get a equals 3 and b equals 17. Do we need to have both little a and little b? We have more variables than equations. We don't need little a and little b. Little b is extra. If you want little b to be 6, I can just adjust a by subtracting 6 from it. So little b provides nothing useful. So we might as well get rid of it and have a simple thing to look at. So b is not needed. Is it wrong to put in b? No. It just makes your life more complicated because you now have a harder function in the numerator than you would have before. And so this is why this is one of the things that's often confusing when people do partial fractions is how do you figure out what are the candidates in the numerator? Well, the candidates, it's 1 degree less than the base polynomial. If I have the x squared, I don't really need the bx plus c, I just need the c. Because whatever that b is, I can adjust a and incorporate it. So it doesn't really allow me to do anything that I couldn't have done otherwise. This is not a complete theoretical proof of whatever polynomial I give you. This is not needed. This is enough. If you want a more theoretical proof, I'm giving 1 out of every 3 classes for applications, advanced theory. If somebody wants to, we can do that. If you want to come to my office and talk about it, absolutely fine. To me, this is enough detail to give you a flavor of what the technique is and to give you something, okay, this is reasonable. But I am at least being honest and telling you, where am I not fully proving something? I'm not fully proving it because looking at how much class time we have more than you would in a normal class because you're all doing great jobs of watching the videos before coming here. It's still not worth the class time to go through it. Class time is better spent describing why we're not going to use class time to do it than to actually use class time to do it. And this hopefully gives you a sense of, okay, I see it. The other thing is, what is the purpose of partial fractions? Why do we learn partial fractions? To simplify it, we'll be more specific. What are we trying to do? We're trying to integrate. So what if every single time you do things, if you never take a b term there, you always get the answer? This is more, are you willing to be like an engineer or an economist and just accept that the math works? And just when you actually go ahead and do it, it just works every single time. It's nice to know why it works so that you know it will keep working. But every problem you use this method on, it will work. And so if you don't put in the b over there, you're never going to see a problem where there will be trouble. Okay. Any other questions on this? So I might have slated, I can't remember, a 3rd class